morning, or good afternoon, or even good evening, depending on where you are, to all of you out there at the screens. On behalf of Miele Professional and DWK Life Sciences, I would like to welcome you to our today's webinar here in our Miele Professional showroom in Gütersloh, Germany. Our goal for the next 60 minutes is to let you explore how high-quality glassware and automated cleaning can enhance your lab processes. My name is Matthias Schmitz. Usually I'm responsible for marketing, sales and service for Miele Professional in Asia Pacific, Middle East and Africa, but today I have simply the honor to be your moderator and guide you a little bit through the next 60 minutes. Let me introduce our experts who will share their insights with us today. The first one you're going to see and hear is Edmund Lowe. Ed is product manager at DWK Life Sciences, is based in the UK and will join us today online to focus on the specifics, certificates, quality criteria and reprocessing requirements of high quality lab glassware. So welcome Ed. The second part will be done by Ramona Diekert and Michael Zedlak here live on stage. Ramona is product manager for laboratory solutions at Miele Professional, and Michael has been responsible for Miele Professional's product management for laboratory, dental and medical for more than 20 years, is member of the expert group AK Lab and is co-editor of the laboratory glassware reprocessing publication, which you will see later on. So you see, we have a great wealth of expertise here today. And now, enough of housekeeping, enough of introduction, let's jump into content now. And Ed, that means for you, please, would you take over and guide us through the specifics of high quality glassware?
Hi Matthias, thank you very much for the kind introduction. I hope everyone can see the screen and can hear me okay. So thank you again for the introduction and for giving DWK Life Sciences the opportunity to present on glassware safety tips and tricks. My name is Ed, as Matthias has mentioned, and I'm the product manager of Lab Essentials and Volumetrics based in the UK. And I will be presenting on behalf of DWK Life Sciences today. So safety in the lab has always been a core focus for DWK Life Sciences. In this presentation, we'll explore how safety begins with quality laboratory glassware. High quality glassware ensures chemical resistance, temperature tolerance, thermal shock resistance, and mechanical durability. These attributes are essential for frequent and effective cleaning, compatibility with lab washers, and maintaining hygiene and sample integrity. So ultimately, they help extend the lifespan of your glassware and support a safer, more reliable lab environment. DWK Life Sciences are a leading global manufacturer for laboratory glassware, life science and pharma packaging solutions. We're a supplier of leading laboratory plasticware, owner of some highly recognized brands. We have almost 2,000 employees worldwide, working across 13 of our manufacturing sites and distribution centers globally. And we have over 30,000 products in our portfolio. DWK Life Sciences traces its origins back to 1887, when Otto Schott revolutionized glass manufacturing with the invention of borosilicate glass. Over the years, through a series of mergers and acquisitions, we have evolved into a company known today as DWK Life Sciences. Now let's move on to an introduction to glass. In this section, we'll cover the types of glass and composition, features and benefits of glass, and also some properties. There are two main types of glass commonly used in laboratory glassware. The first is soda lime glass, as you see on the left-hand side of this slide. Soda lime glass is typically used for disposable items like pastry pipettes and culture tubes. Its applications generally do not involve heat and do not require high chemical resistance. The composition of soda lime glass is relatively simple, consisting of sand, sodium hydrogen carbonate, otherwise known as soda, and also calcium oxide, otherwise known as lime. On the right-hand side of the slide, you see borosilicate glass, which is the preferred material for most laboratory glassware used to manufacture a wide range of products, including beakers, volumetric flasks, and chromatography vials. Its key advantage lies in excellent thermal and chemical resistance, making it ideal for heating and handling solvents. Unlike soda-lime glass, borosilicate contains boric oxide, which imparts elasticity and enhances durability. On this slide here, on the left-hand side of the spectrum is soda-lime glass, as mentioned before, which is a relatively high coefficient of expansion of around 9. This makes it less suitable for applications involving heat or rapid temperature changes, as mentioned before. Its composition and properties are not as tightly regulated compared to borosilicate glass, as you can see in the middle and the right-hand side of the spectrum. Because borosilicate products are highly regulated by ASTM, USP, and ISO standards. Borosilicate glass is available in 2 classifications, 3.3 and 5.1, which refer to its coefficient of expansion, or COE for short. The COE measures how much a material changes in volume when exposed to temperature variations. A lower COE indicates better resistance to thermal stress, making the glass less prone to cracking under sudden temperature changes. For this reason, borosilicate 3.3, as seen on the right-hand side of the spectrum, is the ideal choice for ensuring safety and quality in laboratory environments, owing to its lower COE. It has been tried and tested in the pharma industry. It's tightly controlled and has high purity as defined by the absence of heavy metals, for example. So ultimately, borosilicate 3.3 glass provides superior safety, quality, and data integrity. Glass has some great characteristics all combined into one single material, which means you can use one container for many purposes. So, for example, it's highly transparent. So historically, alchemists used glass to observe reactions taking place inside the container. So, for example, during the transmutation of lead to gold. It has excellent chemical resistance. It's impermeable to gases, which is extremely important to some applications where materials are sensitive to gas. Glass, especially borosilicate 3.3 glass, has very good thermal shock resistance owing to low COE, and it has an even wall thickness if manufactured correctly. You go all the way down to liquid nitrogen temperatures and all the way up to several hundred degrees. As a material, glass forms a rigid, strong, and stable container. Now we'll look at the sort of structure and network of glass, giving it its inherent properties. So glass has a highly disordered amorphous network that is neither liquid nor solid. There are pros and cons to this amorphous network. The advantage is that during manufacture, when heated, it's soft and flexible, so it benefits manufacturing. The disadvantage is that within the amorphous network, the glass doesn't contain planes of atoms that can slip past each other to relieve stress, making the glass brittle. When exposed to excessive stress, it can form cracks and fractures and even lead to surface flaws or the glass to explode if not handled properly, leading to injuries. So the big question here is, how can we avoid damage or avoid adding stress to the glass during routine lab usage? Well, the answer is through best practices and the use of safety products. So the first step is that when the glassware arrives, or before you use it for your experiments, the user should inspect the glassware first before doing anything else. So we would recommend wearing PPE, so protective equipment, to protect your eyes, your face, and your skin. Use a black and white backdrop and flicker-free lights to improve visibility when inspecting the glass, and you want to look out for any flaws in dimensions, chips, cracks, and blisters. You see some common failure modes here in glass, including cracking, fracturing, surface flaws, abrasion, thermal shock, corrosion, and even explosion. We will now look at ways in how we can mitigate the risks associated with glassware. So to mitigate risks from mechanical stress, you basically want to avoid glass-to-glass contact and keep the items upright. So by doing so, we mean to place the items on shelves where possible, or in cupboards, to keep the items away from shelf edges to reduce the risk of knocking them over. Use bubble wrap or cardboard compartments to keep a distance between the items to avoid collision. Avoid scratches from tools such as wire brushes, abrasive pads, and metal spatulas. Use tools and clamps that are plastic or rubber coated to avoid scratching of the glassware. And you should clamp the glassware properly, carefully and gently in the right position to avoid stress. This is particularly important for something like a volumetric flask, as you see here in the slide. When performing HPLC experiments, as we find in many laboratories that we visit worldwide, is that users tend to tilt and tip the HPLC bottle, which is not a good practice. You should be using a product with a conical base reservoir to avoid falls and spillages. So as you can see here, the left-hand side is malpractice, the right-hand side is the best practice using the reservoir. And here you want to be using a bottle carrier to provide a safe and convenient way of transporting bottles and controlling the pouring of liquids. You want to choose products with an ergonomic design. Where applicable, you might want to consider using Super Duty glassware that have a reinforced rim designed for mechanical strength. And they very often have reinforced walls as well to make them mechanically stronger. And the user feedback very often is that they're better for lab washers to avoid sort of damages from mechanical stress and glass-to-glass contact. Where possible, choose flasks with plastic hose connectors rather than glass to avoid breaking of the arms, leading to broken pieces of glass. We find this to be a very common failure mode within laboratories by using side arms that are made from glass. Last but not least, when using filter flasks with glass arm, gently work the tube on and off with gloves on and lubricate the side arms if necessary. Another tip to mitigate the risk from mechanical stress is to use polymer coated glassware for added safety. The coated glassware helps prevent scratches and glass-to-glass contact. And if the glassware is dropped, it holds the pieces together. This gives you an extra period of time to safely transfer the contents into a new container should you drop your bottle. This is particularly important when you have a container worth of, that holds samples that are very expensive or extremely hazardous. Now we move on to ways in which we can mitigate the risks from changes in temperature. So first of all, it's important to note that premium borosilicate 3.3 glassware can be heated up to 500 degrees Celsius for short periods, but you should try to refrain from heating above 400 degrees C. The user should apply a gradual, stepwise and uniform heating and cooling to avoid thermal shock. Hot glass, they look the same whether they're cold or hot, so beware. Always, avoid touching the glassware without, unless you've made sure that it's safe to do so, or as a bare minimum, you should at least wear gloves or use tongs to prevent burns. Use a water bath where possible to optimize heat distribution and uniformity of the heat across the glassware. If using a hot plate, use either a low or medium heat setting because a high heat setting can cause excessive localized heating, creating hotspots. If heating glassware over an open flame, which is still possible at primary schools, for example, secondary schools, use a wire gauze to help diffuse the heat to protect the glassware. But as mentioned before, where possible, you should really be using a water bath or a hot plate to evenly distribute the heat across the glassware. Despite the benefits of Super Duty's mechanical strength, as mentioned earlier, if you're using the glassware to heat for heating applications, use a standard piece of equipment. So, for example, a standard beaker and not a Super Duty beaker. Super Duty beakers are better for mechanical performance, but not so much for heating applications. Bear in mind also that the even distribution of the wall thickness is really important, because irregular wall thicknesses can cause higher stress when heating and cooling. The higher the tension, the higher the risk of glass breakage. So this is why you need a manufacturer that manufactures glassware consistently. For mitigating risks from chemical applications, borosilicate 3.3 glass is an excellent choice because it resists most chemicals. Only highly aggressive chemicals at elevated temperatures, such as hydrofluoric acid, phosphoric acid, and strong alkalis, can degrade the glass. When cleaning with alkali-based agents, keep the temperature at around 70 degrees and use short cycles. Also avoid glass-to-glass contact in lab washes, as this can cause damage to glass equipment. To mitigate risks from pressure applications, use pressure or vacuum-rated products to enhance robustness and safety. When autoclaving, some liquids are prone to foaming, so only fill the container to halfway or 3/4 capacity to allow for liquid expansion to prevent any overflow. When autoclaving bottles, the screw cap must be loosely fitted with a maximum of 1 turn applied, because if you tighten the vessel too much, there's a risk of the glassware exploding. When cleaning, inspect before use, as mentioned before. Try to use an automated washing machines, as the Miele team will bring out the benefits later. Don't use abrasive cleaners, and don't use strong alkalis or strong acids as the cleaning agent. For the very last slide, here is an example of a typical automated reprocessing program. In the cleaning stage, your glassware will be exposed to cold or hot water with alkaline cleaning chemicals or even acidic neutralizers. When rinsing, different water types can be used, and when drying, the temperature can go up to 100 degrees Celsius. This is why you need glassware to provide high chemical resistance and resistance to low and high temperatures, and also high thermal shock resistance. These properties stem from quality, which lead to safety and process improvement. There is nothing more important than making sure that everyone goes home safe at the end of the working day. So here's a summary of what we've spoken about today. And to keep in touch, please feel free to visit our websites and contact us via social media channels, or even contact me directly at edmund.low@dwk.com. And please feel free to use the Teams Q&A function to leave any questions. I'll be happy to answer them for you. So thank you again for listening, and I now hand back to the Miele team.
Thank you, Ed. Thank you
for all the valuable explanations about borosilicate glassware. Dear guests, in our chapter 1 of our webinar, you have learned about the specific of borosilicate glassware and its advantage for all labs. In our second chapter now, we want to talk about the processing of laboratory goods. We will make you familiar with the main principles of lab glassware reprocessing processes, and we will also mention which factors can have a positive or a negative effect on cleaning results. Let's start with a very basic question. Why do we process lab glassware? It's pretty obvious. We need it in labs for conducting the next tests and analysis. So it's really a precondition for every professional lab, every day. But what does it mean? When you speak to lab people, most of them specify what they want to achieve with, I want to produce analytically cleaned lab glassware for my next analysis. And our definition of that is, clean means free from soiling, and dry and spot-free means we have no residues of water or chemistry, for example, on the surfaces, so that we really have pure glassware afterwards. With that, we come to the question, what is clean? So what is the cleaning level we want to achieve? And it's pretty obvious that we want to remove all the rest of soiling, rest of consumables we have been used in processing lab glassware, also rest of water from the surfaces, so that we generate pure glassware that can be used for the next test. And there are different definitions about the cleanliness level. Some say, okay, I'm totally fine if it's visibly clean. Others say, okay, I want to count really the rest of soiling, for example, that remains on the surface with parts per million. So you really count each individual spark, for example. And some other labs also use TOC, which means total organic carbon. That's the rest of organic carbon that still remains on surfaces. Most labs decide to say visible clean is really the level I want to achieve when I reprocess a lab glassware, and so we put a focus on that level in our webinar today. But laboratory glassware reprocessing is really a challenge. And why is that? On the one hand side, we want to, of course, achieve a thorough cleaning, but at the same time, we want also to use a process that is as gentle as possible to the glass items. And that's really important because we want to preserve the value of these goods. It does not help you if you use, for example, a very aggressive cleaner to achieve this thorough cleaning, but at the same time you wash away the scaling of a measuring cylinder, then you can really throw it into the trash bin and you lose really the complete value and you burn money. That is not what you intend to do. During our webinar, you will learn how to really achieve both objectives, thorough cleaning as well as gentle cleaning. And it's a challenge also when you think about all the different items of glassware. You see some most frequently used glassware like beakers, for example, flask, bottles, and some other equipment. Also sometimes in addition with viscosimeters, special glasses that are more an exceptional glassware in daily use. But it's a challenge really to achieve always a good cleaning result. And looking into the details of a specific glassware, for example, the bottles, you see that also this scales up from very small lab glassware up to very big one, to 20-liter bottles, for example. And it's very easy to understand that the method of cleaning those things has to differ. And you have to consider the material that you process. It's pretty clear that, for example, all the equipment made of borosilicate glass is more resistant to heat and chemistry than, for example, goods made of plastic. And not to forget the diversity of soiling. So you have many things you want to wash away during a process That can be lime scale, can be oils, fat, waxes, agar, for example, culture media, marker labels, or microorganisms, for example. So there are lots of different little challenges you have to cope with. And to make you familiar with the main principle of cleaning, I want to introduce you to the Zinner's circle. Herbert Zinner was a chemist in Germany, born in 1900, and he was the first one really stating it does not matter what you clean and how you clean, you always have to consider that this process contains of these 4 factors. Factor 1 is the temperature, and it's pretty clear that warm water, for example, cleans better than cold water. You will have experienced that also when you wash your hand, for example. Secondly, we have to consider mechanics. Mechanics means that we have to bring on in a cleaning process a certain force, for example, with a water spray onto the surface to really remove the soiling. And that is also, the more force you use, of course, the easier or the better the cleaning result will be. The third one are the consumables, detergents. There are hundreds of detergents available in the marketplace, and we can distinguish between high-performing or low-performing detergents. And last but not least, you have to consider the time. It's also very clear that the longer the process takes, and you can extend the exposure time, the better the results will be. And the important thing now to understand is that all these 4 factors work together. It's an interplay of all these factors. And it's possible to reduce the impact of one factor. For example, when you decide that you want to save energy and decide therefore to have a cleaning process done with 40 degrees Celsius instead of 55 degrees Celsius, for example, then you can do that. But at the same time, to achieve the same cleaning result, you have to extend at least one of the other factors. For example, you bring in more mechanics, so mechanical force, with more water pressure, for example, or you use a more performing detergent, or you can also decide to have a longer exposure time. And that also works vice versa, but the main takeaway for today is please consider always that you have to count with these 4 factors. And water is, of course, the most important media when we talk about cleaning, because water is still a very cheap media in the world, so it's the most used media for all cleaning processes on the globe. But there are different water qualities. For example, when you want to use tap water or drinking water, can be cold or can be warm, then this is the cheapest way of reprocessing lab glassware, but does not provide always ideal results at the end, because it has a certain hardness, and that is always a kind of limitation for achieving good cleaning results. That's why many labs use softened water. Can also be cold or hot, and in this process of softening water, we take out the components that are responsible for the hardness of water, and with lowering the hardness degree, it makes it much easier to resolve all the cleaning problems and to really to flush away the rest of the soiling. And last but not least, what is recommendable is also for a final rinse step to use demineralized water. Demineralized water means this is water free from nearly all the minerals that water normally contains. And with that, after the drying phase, you really achieve brilliant results. That means you will not detect any kind of gray or white spots that normally you will find when you just use tap water or softened water for the whole process and do the drying. Yeah, speaking about water quality a little bit also with figures. When we speak about soft water, then we speak about the total hardness of less of 4 degrees German hardness. That means this water contains less than 70 milligram of calcium carbonate per liter, And that is one important factor. And the other important factor we would like to emphasize on is that the chloride content should not exceed 100 milligram per liter as well. How you can find out if your water meets these characteristics, you can ask your waterworks. They can provide you with the data for your tap water, of course, but you can also use very simple tests to measure the water hardness, for example. Secondly, I want to also stress the fact that detergents are a very powerful factor within cleaning processes. And we distinguish between cleaning agents on the one hand side, and it depends a little bit on the soiling. If you have to use acidic detergents, for example, when you want to wash away limescale, that is recommendable. And the characteristic of acidic detergents is that the pH value is very low. It differs between 2.5 up to 5. So it means really it's an acidic environment, and that is helpful for flushing away certain soiling. Then we have neutralizers or neutralize detergents. So that means it ranges pretty much between 6 and 8. With that, it's not very aggressive, so it does not really cause harm to the items you reprocess, but the cleaning performance is also limited with that. Most common to use is for many soiling to use mild alkaline or high alkaline detergents that range between 9 to 11.5 in the pH value, because this is really helpful to solving all cleaning problems that occur when you have standardized soiling in your lab glassware. But when you use them, it's also recommended to use a neutralizer. That's the second group of consumables I want to touch on, because the neutralizer after the cleaning phase bring down the pH value in the neutral level, and that is very important also to be as gentle as possible to the goods you reprocess. And then that sometimes is necessary, you can have certain additives like surfactants, emulsifiers, oxidant agents, or defoaming agents. These can be used really to optimize the process so that you can really at the end achieve very good results. But these are exceptional components. You don't to use them in everyday cases. This is maybe very quick information on all the factors and what to consider. I know that this is not very easy to understand when we only have a few minutes for these important topics, but don't worry. You see here a table that is part of this brochure that Matthias already mentioned. It was generated by a special working group, and here you find some pages where you see for the different forms of soiling which kind of consumables are recommended to use in the cleaning process. And we make this brochure available in a digital format, and Matthias will explain how you can get access to this brochure. And this brings us to the third chapter of our webinar. And my colleague Ramona will now introduce you to the different methods how you can do cleaning, and also speak about the advantage or disadvantage of the different methods.
Thank you. So thanks, Michael. So the question is, how do we actually now clean laboratory glassware? And there are generally two methods. So we usually have manual cleaning with water, tap water, with cleaning agent, and using brushes or suitable sponges. And then alternatively, some labs also use ultrasonic bath with cleaning agent as a form of semi-automated cleaning. And then the alternative from manual and semi-automated cleaning is cleaning with a lab washer, so automated cleaning. So what is a professional lab washer? Let's take a look. Yeah, luckily we are in our showroom here in Gütersloh today. And here I have one example of a lab washer. This is our Explore line. It's our PLW 8604. So it's a lab washer specifically designed for labs that want to move from manual cleaning to something that is more efficient, to something that is more reliable. So the Explore line comes with 2 loading levels. And what you see here is one of our most popular configurations. So we have in the upper basket, we have 2 inserts for beakers. And then in the lower basket, we have 2 easy load modules to clean narrow-necked glassware. So this is, these easy load modules, they work with injectors that you can see here, and they properly clean the inner surface of the glassware. And the good thing about the easy load system is no matter how you place the glassware on the injector nozzle, it always finds its way to a perfect position for cleaning. So you always have the perfect position for the glassware on the injector nozzle. Yeah, so with this configuration that you see here, you can clean up to 60 glasses, so 24 beakers in the upper basket and 36 narrow-necked items in the lower basket. So that's our Explore line model. And it basically has everything a reliable lab washer needs. But of course, in the laboratory sector, there are many different requirements. We have many different applications, so there are different requirements for a lab washer. And what you see here in our showroom are other models. We have on the right side, from my side on the right side, there's an under-counter model. That's our expert line model. It's not now seen very well, but it is the expert line model is our solution for all types of laboratories, even the most demanding application, the most demanding requirements. And what is behind me is our slimline model for laboratories that require greater capacity. It has up to 4 loading levels, and everything on a relatively small footprint. So there's a lot we could talk about today regarding the machines, but that's not our topic. So I would like to move on with one of the questions that we receive quite frequently when we talk about lab glassware cleaning, and that is why, or if we could use a dishwasher instead of a lab washer for cleaning glassware. And the short answer is no. It's a dishwasher is not suitable to clean lab glassware. And here are some of the reasons. First of all, it's not approved for lab standards or for safety standards. For example, the European Machinery Directive, a lab washer does not approve. Then dishwashers are not designed for professional use. As Michael mentioned earlier, in lab glassware cleaning, we use different cleaning agents, acids for neutralization, and these can damage the internal components of a domestic dishwasher. The valves, the dosing system, they are not built for these substances. Domestic dishwashers also have a much weaker pump. So they are designed for dishes and not for cleaning complex laboratory glassware. So the water pressure, the water flow is not sufficient for lab glassware. Dishwashers also lack special programs, so that are sometimes needed for cleaning different contaminations or different types of glassware. And the loading system is not ideal for glassware. So as shown in the clip, the glassware is not held securely in place in a dishwasher, which has a huge effect on the cleaning result. And also domestic dishwashers lack injectors, which is essential for most lab applications. So to sum it up, a domestic dishwasher does not meet the requirements for properly cleaning lab glassware. Now, there are many different aspects that play a role in lab glassware cleaning, and here are some of them. And to really understand the difference between manual cleaning and automated cleaning, we now take a look at these factors, starting with the processing results. So when we wash glassware by hand, the cleaning results can vary significantly from day to day, from person to person. So on some days, the glassware comes out spotless, and on other days we might miss a spot, or we skip a rinse if we are in a rush. And manual cleaning is never completely consistent because so many parameters change. So that the cleaning agent reach the entire surface of the glassware? How often do you rinse? The temperature of the water. So this inconsistency in these parameters means there is a higher risk for insufficient cleaning and remaining contaminants on the items. And even if you have small residues on the glassware left, it has an effect on the sterilization, if you sterilize the glassware afterwards, and on the next test results. So also some type of glassware are difficult to clean manually. Narrow-necked items, for example, pipettes, viscometers, HPLC vials. There's always a higher risk that residues remain in these tighter areas of the glassware. Let's take a look at automated cleaning. So here we have from pre-cleaning to cleaning, rinsing, and drying, a completely controlled process. So each program automatically uses the correct temperature, the correct water pressure, the dosing. It's all aligned in a way to achieve the best or the highest cleaning result. So what Michael talked about earlier with the Sinner circle, it's aligned perfectly for each program. And the big advantage here is the consistency. So with every cycle, we have the same high quality of cleaning result. No matter who operates the machine, no matter what day it is, you always have reproducible results, validatable, that are validatable. And when it comes to complex glassware, these narrow-necked items, it's not a problem for a lab washer. As we saw earlier, or here in the clip on the side, we have our easy load system where the water flow or the flow of the process chemical, the water is distributed very evenly, very effectively to clean the glassware that we see here in the little animation. So how does the cleaning method, or in this case manual cleaning, affect the lifetime of the glassware? Washing by hand is surprisingly harsh on the glassware, or can be, due to chemical and mechanical stresses. So if the glassware is exposed too long to alkaline cleaning agents, strong alkaline cleaning agents, it can lead to glass corrosion. And the same if you brush the glassware improperly or you use the wrong brush, it can cause scratches, and also have an effect on the durability of the glassware. With automated cleaning, the cleaning is much more gentle. The process parameters are defined in a way to create as little stress on the glassware. We have short contact times with alkaline cleaning agent, and the mechanical stress is very limited. As we see in the video on the side, the positioning of the glassware is stable, so it leads to a longer lifetime of the glassware, and in general, reduced replacement costs per year. Let's take a look at the safety aspects. So in manual cleaning, you have many different steps: pre-cleaning, scrubbing, rinsing, drying. And with every step, the individual who's doing the cleaning is exposed to different possibly toxic substances, infectious substances from the residues, but also they are exposed to the process chemicals for cleaning the glassware. So there is a higher risk for burns, for allergic reactions, or other health-related issues. And in general, we have then a higher risk for the stuff in manual cleaning. In automated cleaning, your only role is to load the washer and to unload it. So there is there's less contact with harmful substances, and overall a reduced risk for the stuff. Now let's take a look at sustainability, and I have a question for you. What do you think? How much water is needed to clean 60 regular lab glasses? And with regular, I mean beakers, flasks, so nothing complex. So how much water do you think is needed to clean them manually and with a lab washer? You can take a guess and put it in the chat if you like. I will give the answer immediately. So here in our tests for 60 regular lab glasses, it took 81 liter. And that is tap water plus the eye water. So for automated cleaning, it took us 32 liter with a lab washer, and that is 63% less water with a lab washer. So if you calculate that for a year, so cleaning 60 lab glasses each work day for a year, you can save around 8,700 liter of water. So think about 8,700 1-liter bottles. That is a lot of water that you can save. So a lab washer can really enable laboratories to become more sustainable. Let's move on to efficiency. So how much time do you think is needed to clean 60 regular lab glasses? So manually and automatically. In our tests, it took 58 minutes. So 58 minutes cleaning them manually, and with a lab washer, with our Explorer line in the standard program, it takes 24 minutes. So that's, in this case, 59 minutes, 59% less time with a lab washer. And again, if you calculate that for a year, you can save around 156 hours. And that's, with an 8-hour shift, that's 19.5 work days that you can save with a lab washer. And so that is almost a complete month of working that you can save using the throughput that we have here in the example. But there's another aspect in terms of efficiency. So when it comes to someone spending 58 minutes a day at the sink, that's almost an hour lost per day in productive work. And with a lab washer, you just load the lab washer, you press start, and then you can go away to do something more productive. So in many labs, staff time is very critical and a valuable resource. So shifting these 58 minutes manual cleaning to something more productive can be a big gain for a laboratory. So we covered many aspects by now. Let's take a look at the cost efficiency. Is automated cleaning actually cost efficient? Imagine a university laboratory where we have various applications, and a large proportion of their glassware is used for simple water-soluble residues. We have 120 beakers and flasks per day that they currently clean manually. for 250 days a year. So for this lab, our Explore line model that I showed you earlier could be a good choice, together with the accessory set that you have seen. So to evaluate whether the investment makes sense for this university, we considered personal costs, water costs, process chemical costs in manual cleaning, and in automated cleaning also energy, service costs, and the initial investment costs in the lab washer, as well as the accessory set. So here the cost development over 8 years. If we look at the gray line representing manual cleaning, we see very low initial costs. So all you need is a brush, some cleaning agent, but over time, the gray line adds up, mainly because of personal costs and process chemicals. Now let's turn to the red line, representing automated cleaning. Here there is a higher initial investment in the lab washer and the accessories, but once installed, the operating costs, they rise much slower, thanks to the personal costs, thanks to the resource costs. And the two lines cross at about 1.6 years. So that's the break-even point. That's where the lab washer pays off. And it continues to save money over the coming years, over the product lifetime of the machine. So I hope by now you see how valuable automated cleaning really is, and how it can enhance your lab processes significantly. It delivers better cleaning results, consistent cleaning results that manual cleaning just cannot do. The cleaning with the lab washer is much faster. It frees up time for more important tasks. It uses significantly less water and optimizes the consumption of process chemicals. It helps to extend the lifespan of your product, the glassware. And it offers maximum protection for the staff, as we saw, that they are exposed less to harmful substances, to broken glass. And even with a higher investment that we just saw, a lab washer pays off very quickly and delivers long-term savings. So to wrap up this section of the webinar, I would like to summarize with a little video that addresses some of the benefits that we talked about before we go into the Q&A session together with Matthias. So thank you.
All right, 1 hour goes by very quickly, and you have seen all the presentations now, so from Ed, from Michael, from Ramona, and we are here now for the Q&A session, and you already see I brought the expert with me directly. We saw a few questions in the chat. There was one with regard to storage of the glassware, which Ed answered already in the Q&A part of the meeting here. So I think that was sufficiently answered. Thank you very much again, Ed, for answering that so quickly. Then there was another question, which basically went like, our lab has a variety of labware we regularly have to wash, not just glassware. And then there were a few examples of different items to be washed. Can the Miele lab, and the question then is, can the Miele lab washer be used for cleaning all the different labware, and what is the capacity and the program runtime? And my answer would be simple, yes it can, but as this might not be very sufficient answer, we have now Michael here who can elaborate on that by far more than I can.
Yeah, thank you. Yeah, to answer your question, Sandy, of course we provide customers, if they want, with a huge variety of baskets, insert modules that can be used with a small device, but also is suitable to use in a mid-size or large device. The concept that we have since many years is that we want to provide customers with flexible basket concept, so that can be adapted to all the needs that you have. And especially when you have to reprocess a huge variety of labware, then you need this kind of flexibility. And it works like that. You see on the one hand side, you have baskets, here in this example, a top basket and a bottom basket. And always you have modules that fill half of this level. And you can decide which kind of inserts you want to use for this specific labware. And in our brochure, you will find a lot of items that can be used to do this configuration for your specific lab. And when you see that on page by page, you see a lot of these modules that can be selected and used. And changing a module is very easy. It's not connected with screws, for example, to the basket. You can very easily take it out without any kind of tool and put it in another module. So you can also change between small scale lab glassware or large scale lab glassware, for example. And the items you mentioned in your question, therefore we have specific inserts. And it's the question then, of course, at the end, how many units you have of the different sorts of lab glassware you want to process. So in this case, I would also recommend you to get in touch with your dealer who has the expertise really to consult you for the right selection of modules, baskets, and inserts. To the question about cycle times and also capacity. Capacity depends on the size of the machine. That's very obvious. Ramona mentioned to you that we have lab washers of different sizes, and therefore you have different also quantities you can reprocess in one batch. And the cycle time pretty much depends on different factors. For example, the power supply is very essential. If you can really use all the heating elements that are built in our machines, or only a few. So therefore, I can only give you an indication. Machines like that receive very good cleaning results with a program that has a running time of 24 minutes, for example. But then, according to the specifics and the application and also the cleaning and drying result you want to achieve, you can also have extended programs. For example, on board you will also find for many lab washers an intensive program. If you find a soiling that has been dried maybe over the weekend and things like that, then you would have to extend the cycle time. That's pretty clear. I hope that this in short answers your questions, and more, please, for more, please contact your dealer.
All right, yeah, thank you, Michael. Indeed, as I said, by far more comprehensive your answer than just my yes, it can. But there was another one in the chat, another question. What is the product lifetime of the machines?
Yeah. We have a philosophy at Miele that we test all our lab washers for usage time of minimum 15,000 hours. In 15,000 hours, when we just calculate it very simple and say, okay, maybe an extended program that would take 1 hour, that would mean if you do 3 cycles a day, have 250 working days in a year, that would sum up then to a lifetime of 20 years. That is a kind of indication. Of course, if you want to do less cycles a day or more cycles, then of course this value will change. But please keep in mind 15,000 working hours. We test every lab washer for that purpose, and roughly speaking, this is a lifetime of 20 years.
Very good. Thank you very much, Michael. And there was another question in the chat which I will be able to answer. So the question was, will we receive the slides afterwards? So will we provide the slides to you? And this question is a perfect bridge, so to speak, to my last slide and to kind of a summary. But before I do that, just a quick remark. We will keep the chat open. So if there might be more questions now or later the day, just type it into the chat as well, and we will, from time to time over the course of the day, look and try to answer if there will be more questions. But now, as I said, we are almost through for today, but now the closing this webinar is not the end, because within the next 2 weeks we will provide more information to you. So you will receive an email, or through our partners you will receive the information. First of all, a certificate of participation, show the world that you have participated in this webinar here. Then a link to download the brochure that Michael referred to earlier, so that he has also shown you. Or alternatively, of course, you can use this QR code which you see here and which you then also find in the slides and in the video, which we will also provide you. As told you in the beginning, we will record this webinar, so you will provide it with a link to the YouTube channel where you will find the recorded session. And then, of course, as said before, we will also provide you the slides in a kind of probably condensed format, most likely a PDF format, because otherwise it would be simply be too huge, but you will also receive that. And finally then, especially in case you might have any questions later, please refer, and Michael mentioned that already as well, please refer to our local partners who invited you for today as well. And then stay in touch with Miele Professional and with DWK Life Science via our social media channels like LinkedIn, for instance. And with that, I would like to thank you very much on behalf of Miele Professional and DWK Life Sciences, especially Ed, Ramona, and Michael, but also all the other colleagues who were involved in preparation of today's webinar, for attending our meeting here today. Enjoy the rest of the day and stay healthy. Goodbye.